So welcome to Lesson 4. We're on Refraction 1. And we're now on Lesson 4, Part 2, where we're going to look at real and apparent depth. So you can actually see in the picture here on the main page that a fish appears to be shallower than it actually is in water. Because when the light from the fish comes out through the water, the light bends. It has that appearance of being shallower than it actually is. So you've downloaded your notes, and let's go to this section. So, for Part 2, real and apparent depth. So let me have a look at why that appears to be the case. Why does a fish actually appear to be shallower than it actually is? So here I have a body of water, and I've got an object at the bottom of the lake. And I'm going to have someone outside here looking into the lake. So the question is, why does that object appear to be shallower? It might be somewhere up around here rather than down there. So let's have a look at why that is. Well, there's going to be millions of rays of light coming off that object. All I want are 2 rays. So let me take a random ray. So here's a random ray coming out. So it travels straight up through the water. And then, when it hits the surface, what's going to happen to it? Well, let me put my normal in. So here's my normal, which is a ray of light, which is a line perpendicular to the surface. Now, I'm going to be moving, that ray of light is going to be moving from a slower medium to a faster medium. It's going to go from water out to air. And what happens to it? It'll bend away from the normal. So that ray of light will bend away from the normal. Let's say like that. When you're doing this drawing, actually, just do a broken line going back to that black broken line there. So there's one ray of light coming from the object. You can see it bends away from the normal. There's your angle of incidence there. And there's your angle of refraction. That angle of refraction will be bigger than the angle of incidence. Let me take another ray of light. So another ray of light from that object. It goes up through the water. It hits the boundary. Let me draw normal in, a line perpendicular to the boundary. And that ray of light is going to bend away from the normal. Now, we're not going to do the calculations, but if I want to get my diagram spot on, I'm going to put my ruler here, and I'm going to join it up so it goes back to where that broken line hits the black broken line. So it bends out like this. If I work it backwards, those rays of light will meet there. So if you're somebody who's viewing the fish, here's your eye here. Those rays of light coming out from the fish are diverging, but in your mind's eye, you work them back to where they met, and they meet back here. So there's the image eye of the fish. So the object, the fish is actually down here, but the image appears to be up here. The real depth is a depth from the top of the water down to the bottom of the lake, where the fish is. The apparent depth, where the fish appears to be, is from the top of the lake down to where the image appears to be. So down here, this is what we call the apparent depth A. So I'm calling R the real depth, and I'm calling A the apparent depth. Now, there is a formula. We're not going to prove the formula, but it'd be very easy to prove. But the refractive index of the water, NW, A is the letter that should be there. In other words, we mean going from A to W, but the air is assumed. So NW is equal to the real depth, or divided by the apparent depth A. So there's a little formula that we're going to use. That formula is actually not in your table book, so you'll have to learn it. But if I have a look at it in your notes, there you see that formula in your notes. The refractive index N is the real depth or divided by the apparent depth A. There's a real-life application here. Well, we've already talked about it. The real-life application for real and apparent depth is when you look into water, objects like fish appear to be shallower than their actual depth. So that's really important if you're diving into water and you see the bottom of the pool. The bottom of the pool actually appears to be shallower than it actually is. So one needs to be very, very careful of that when diving into water. So let me do an example on that. And the example is there. Example number 7. A fish appears to be 12 meters below the surface of a pond. That's the apparent depth. What is the real depth? Or we're given the refractive index of water is 4/3. So let me have a look at this question in detail on the board. So a fish appears to be 12 meters. So the apparent depth A, 12 meters. And they're asking me what is the real depth or. And they've told me that the refractive index of water is 4/3. So write down my formula. The refractive index is real depth divided by apparent depth. The refractive index is 4/3. The real depth we're looking for, and the apparent depth is 12 meters. So the calculations are extraordinarily simple. So work out your value of R. So slide the 4 up. So R is equal to 12 by 4 divided by 3. And my answer when I do that calculation is 16 meters. So the real depth is 16 meters and the apparent depth is 12 meters. So let me develop that now and go on to the experiment we do on real depth and apparent depth. This experiment is actually called L3, but they've never ever asked it in the Leaving Cert. We'll talk about it anyway. How do I measure the refractive index of material in the lab? Well, I use something called a traveling microscope. So a traveling microscope is a microscope that moves up and down along a scale. That scale there is called a vernier scale. And by moving it up and down, I'm going to focus on different objects. Let's say, for example, you wanted to find the refractive index of glass. Well, the first thing you do is, there's the surface of a table, let's say, and I'm going to focus on an object or a mark on that table. So let's say we put a black mark on that table. You're going to move that telescope, that traveling microscope, should I say, up and down, until that becomes sharply in focus. And you're going to take a reading off your vernier scale. And we'll call that reading there, we call that reading R1. Then what you're going to do is, you're going to put a block of glass on top of it. So let's say, I take a block of glass. So here's my block of glass. And I'm going to put it down on top of that mark. Now you're going to focus it on it again. But you see that mark there? That's going to appear shallower than it actually is due to the refraction of light as explained in the last diagram. So when I focus on it again, the mark may appear to be here. So I'll call that reading now R2. So I've got to adjust my traveling microscope, and the new reading on the vernier scale will be R2. And then finally, I'm going to focus on a mark on the surface of the glass. I'm going to have to adjust my traveling microscope again. And that third reading I get will be R3. You know, you could also do this with water. So if I did it with water, I would take, for example, a container of water. So let's say, here's my container of water. Well, first of all, take a container. I'm going to move my traveling microscope over there. I'm going to put a mark on the bottom of the container. I'm going to focus on that, and that reading will be R1. Then I'm going to fill my container with water to whatever depth I want. So put some water into your container. And then when I focus on that mark again at the bottom, it's going to appear shallower than it actually is. So it may appear here. This reading here will be R2. And then finally, I want to focus on a point on the surface of the water. You can sprinkle some powder on the water and focus on the powder. And that reading there will be R3. And then from those results, I want to work out the refractive index of the glass here and the water there. Well, what's my formula for refractive index? The refractive index of material N is real depth divided by apparent depth. Now, what's the real depth of the glass? The real depth of the glass will be the top reading minus the bottom reading. It'll be R3 minus R1. And what's the apparent depth going to be? The apparent depth will be from the top to where the bottom appears to be. It's going to be R3 minus R2. So there's a formula that we can use using the traveling microscope to work out the refractive indices of materials. So let's go back to our notes and have a look at an example of that. So there's your formula there. N is equal to R3 minus R1 over R3 minus R2. And then here's my example. So a traveling microscope reads 3 centimeters, 5.24 centimeters, and 7.58 centimeters when focused on an object in air. The same object covered by a transparent plastic slab and the top of the plastic slab. Find the refractive index of the plastic material. Okay, so let me look at that in detail. So I've taken down my readings for R1, R2, and R3. So the solution is now very simple. N is, using this formula over here, R3 minus R1. That's the top reading minus the bottom reading. That's the real depth, over R3, the top reading, minus R2, where the bottom appears to be. Just slot the numbers in, leave everything in centimeters, that's fine. So R3 is 7.58 minus R1, 3, divided by 7.58 minus R2 minus 5.24. So let me put all of those readings into my calculator. Fraction button, 7.58 minus 3 divided by 7.58 minus 5.24. So I get, say, about 1.96 is the refractive index of that plastic slab. So the questions are very, very simple. Okay, so that's a really short lesson. The calculations are also very simple. So now it's just over to you to do a little bit of practice. So let me get down to the numerical problems. So far you've done down to number 13 from lesson part 1. And now from this lesson part 2, I just have 5 simple examples from 14 down to 18. So, number 18 you have to do a little bit of thinking about. But they are very, very simple. So get through them before we go on to the final part of lesson 4.